Assalamualaikum, everyone. Today's episode is another application of the Snell's Law of Refraction of Light, focusing on determining the speed of light when it enters an optically denser medium, such as a glass plate, whose index of refraction is given. So join me till the end of my presentation. Watch and learn. The question is, a glass plate 2.50 millimeter thick with an index of refraction of 1.40 is placed between a point source of light with wavelength 540 nanometers in vacuum and a screen. The distance from the source to screen is 1.80 centimeters. How many wavelengths are there between the source and the screen? We have here the diagram that gives us the relative positions of the point source, the glass plate, and the screen. The thickness of the glass plate, denoted by capital L, equals 2.50 raised to the negative 3 meters. And the index of refraction of the glass, denoted by n sub g, equals 1.40. The separation distance between the point source and the screen, denoted by small d, equals 1.80 centimeters. And the wavelength of the light, the incident light in vacuum, is 540 nanometers. And our target variable is the number of wavelengths between the source and the screen. And we denote this number of wavelengths in terms of capital N. We start our computations by determining the frequency of the incident light whose wavelength lambda sub 1 is given. All right? So our formula is simply to divide the speed of light in vacuum divided by the given wavelength lambda sub 1. That is, the frequency f is equal to 3.00 raised to the 8th power meter per second divided by 5.40 times 10 to the negative 7 meter. So when we do our math, we get the value of the frequency f equals 5.56 raised to the 14th power hertz. Okay, this is the frequency of the incident light. All right, and when it enters the glass plate, take note that this frequency f remains constant. The type of medium through which the light travels does not affect the frequency of the light. One of the mathematical equations of the law of refraction of light, or Snell's law, is that the ratio of the speed of light in vacuum to the speed of light in any material medium that it passes through is equal to the index of refraction of the material medium. All right? So, in this problem, all right, uh, we are to determine the speed of light as it passes through the glass plate. And we denote that by small letter v. So small letter v, or the speed of light in the glass plate, is just equal to the speed of light in vacuum divided by the index of refraction of the glass, uh, which is given in the problem. And we denote this here by N2, or that is speed of light in the glass equals 3.00 raised to the 8th power meter per second divided by 1.40. This is the index of refraction of the glass given in the problem. So again, when we simplify, we get the speed of light in the glass plate, V equals 2.14 raised to the 8th power meters per second. So as expected, the speed of light in the material medium or glass is much less compared to the speed of light in vacuum. Now that we have computed the speed of light in the glass plate, all right, we can proceed in getting the corresponding wavelength of light, okay, when it passes through the glass plate. And we denote that wavelength as lambda sub 2, right? And that is just equal to the speed that we have computed, small letter v, divided by the constant frequency of light, which we also have computed earlier, right? Substituting, the wavelength of light, or lambda 2, is equal to 2.14 raised to the 8th power meters per second. That is the speed of light in the glass divided by 5.56 raised to the 14th power hertz or per second, right? That is the frequency of light earlier calculated. So again, dividing these two quantities, we arrive at the value of lambda 2. Okay? Lambda 2 equals 3.85 raised to the negative 7 meters. Okay, rounded to three significant figures. So you will notice that um, the wavelength of light here in the glass is also less compared to the wavelength of light, or the wavelength of the incident light in vacuum, that is. So obviously, at constant frequency, we may say that speed and the wavelength are directly proportional. The main goal in this problem is to determine the number of wavelengths between the point source and the screen. That means the distance d, all right, or the distance of separation between point the point source and the screen, all right, which actually is given as 1.80 centimeters. We wish to find out that distance corresponds to how many wavelengths. And since the wavelength of the incident light is much greater than the wavelength of the light that enters or travels through the glass plate, all right? So there is a need for us to determine the corresponding number of wavelengths, all right, for the distance d, as well as the thickness of the glass, capital L. So first thing, we have to get the difference of D and capital L. That is 108 or 1.80 centimeters minus 0.250 centimeters. All right. And we get their difference, which is 1.55 centimeters or 1.55 raised to the negative 2 meters. All right. We then find the number of wavelengths that corresponds to this distance, all right, of 1.55 centimeters. So we denote that number of wavelengths as n sub 1. And that is just equal to 1.55 raised to the negative 2 power meter divided by 5.40 raised to the negative 7 meters. 5.40 raised to the negative 7 meter, remember, is lambda sub 1, or the wavelength of light in vacuum. Right? So dividing these two quantities, we will get the value of capital N sub 1 equal to 2.87 raised to the fourth power wavelengths. Right? So this corresponds to the number of wavelengths of the distance between the point source and the screen, okay, without including the thickness of the glass plate. Likewise, we also determined the corresponding number of wavelengths for the thickness of the glass plate. Capital L equals 2.50 raised to the negative 3 meter. So using the same method, okay, the number of wavelengths corresponding to the thickness of the glass plate is denoted here by capital N sub 2. So we just divide 2.50 times 10 to the negative 3 meter by 3.85 times 10 to the negative 7 meter. 3.85 times 10 to the negative 7 meter is the wavelength of the light when it passes through the glass plate, or that is lambda sub 2. So when we do our math, we get the value of capital N sub 2 equal to 0.649 times 10 to the fourth power wavelengths. So finally, we can now determine the number of wavelengths, okay, between the source and the screen, denoted by capital N. It's just the sum of 2.87 times 10 to the fourth plus 0.649 times 10 to the fourth, or capital N equals 3.52 times 10 to the fourth power wavelengths, which is our final answer. So that's it. We are done. Till the next episode. Mabuhay. MashaAllah. Thank you very much for your indulgence. Please don't forget to subscribe to my YouTube channel. Alhamdulillah.